Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to your online lecture series of EE314 Measurements in Instrumentation. This is the third lecture of week 12, your lecture number 39. And in this lecture, we are going to discuss about some additional concepts in instrumentation. And this lecture will be a closing to your instrumentation course contents. And after that, we are going to solve some design problems based on different topics. So in this lecture, we are going to discuss about significance, noise, interference, sources of interference, ground faults. So let's get started with our lecture. So starting with significance and statistics. Process control is vitally concerned with the value of variables, as the stated objective is to regulate the value of selected variables. It is therefore very important that the true significance of some measured value be understood. We have already seen that inherent errors may lend uncertainty to the values indicated by a measurement, and in this section we need to consider another feature of measurement that may be misleading about the actual value of a variable, as well as a method to help interpret the significance of measurements. So what are significant figures? In any measurement, we must be careful not to attach more significance to a variable value than the instrument can support. This is particularly true with the growing use of digital reading instruments and calculators with 8 to 12 digit readouts. Suppose, for example, that a digital instrument measures a resistance as 125 kilo ohms. Even if we ignore the instrument accuracy for now, this doesn't mean that the resistance is 125000 ohms. Rather, it means that the resistance is closer to 125,000 ohms than it is to 124,000 ohms or 126,000 ohms. So we are rounding it off to the closest 1 kilo ohm value. We can use the 125 kilo ohm number in subsequent calculations, but we cannot draw the conclusions about results having more than 3 numbers, that is 3 significant figures. The significant figures are the digits, the places that are actually read or known from a measurement or calculation. So we have to be very careful that how much significant figures does our instrument support. Let's explain it further using another example. So significance in measurement is when using a measurement instrument, the number of significant figures is indicated either by reliability in case of analog instruments or by the number of digits in a digital instrument. This is not to be confused with accuracy, which supplies an uncertainty to the reading itself. So we are not talking about accuracy, just ignore the accuracy for now. The following example illustrates how significant figures in measurement and accuracy are treated in the same problem. We have a digital meter that measures current through a 12.5 kilo ohm resistor as 2.21 milliamperes. So that these two are the actual measured readings by your instruments using a 10 milliampere scale. So this instrument can measure from 0.00 milliamperes to 9.99 milliamperes. This is the range at 10 milliampere scale. The instrument accuracy is plus minus 2% of full scale. So the full scale is now 10 milliamperes. Find the voltage across the resistor and the uncertainty in the value obtained. So to find the voltage, we can simply use V is equal to IR. And for I, we are going to use this value, and for R, we are going to use this value. So let's find out. V is equal to IR means 27.625 volts. The current is given to 3 significant figures, so no result we can find be significant to more than 3 digits. And also the resistance is given to 3 significant figures. This means that the value of voltage we are getting here has 1, 2, 3, 4 and 5 figures, but our output that is resulting by multiplying two quantities when both of them has only three significant figures cannot have more than three significant figures. So the actual value of our voltage will be 27.6 volts, and this 0.025 volts is not significant in this case. The accuracy means that current could vary from 2.19 to 2.23 milliamperes because it is plus minus 0.02 milliamperes, 2% of full scale, which introduces an uncertainty of plus minus 0.25 volts. Thus, the correct answer would be 27.6 volts plus minus 0.3 volts, because we must express the uncertainty so that our significance is not changed. What is meant by change in significance when expressing the uncertainty? So our significant voltage was up to 1 decimal point, 27.6 volts. After that, whatever value of voltage was coming was not significant, and our uncertainty was coming to be 0.25 volts. Now this 5 is out of the significance of the actual voltage. So again we have to round it off to match the significance of our voltage, and we have to round it off to 0.3 volts to get the complete correct answer. We don't now don't get confused by the fact that we are going to have three significant figures in the uncertainty also. No, the uncertainty is linked to the significance of the quantity you are measuring. So the quantity will have only three significant figures, but the uncertainty in that quantity is linked to the resolution of that quantity. So I hope this clears the concept of significance. Let's move further. In calculations, one must be careful not to obtain a result that has more significance than the numbers employed in calculation. This is really important. Let's demonstrate it using an example. A transducer has a specified transfer function of 22.4 millivolt per degree centigrade for temperature measurement. The measured voltage is 412 millivolts. So this is the transfer function. This defines the resolution, and this is the actual measured voltage. What is the temperature? We can easily find the temperature by dividing the output voltage with the transfer function, and we are getting this answer, 18.392857 degrees. Now let's see what was the number of digits, significant digits given in our data. So here in the transfer function we are given the transfer function in terms of three significant digits, and here the output voltage was again measured in three significant digits. So our temperature can also have three significant digits, and that is 18.39. So 9 will round off this 3 to 4. So we will have a temperature of 18.4 degrees Celsius. The rest of these numbers are not significant. Our result can be significant only to three places. When a designer is designing some signal conditioning circuit, one should have a very clear understanding that what is the difference in significant figures associated with measurement and conclusions drawn from measurement and significant figures associated with that design. A design is a hypothetical development. It is not a physical design. So first we design the circuit or signal conditioning system by calculations, by analysis, and then we implement it. So that hypothetical development makes implicit assumptions about selected values in the design. If the designer specifies a 1.1 kilo ohm resistor, the assumption is that it is exactly 1100 ohms. And if the designer specifies that there are 4.7 volts across the resistor, then there are exactly 4.7 volts. And the current can be calculated as 4.272727 milliamperes. Now, suppose we measure the resistor when the design is built and find it to be 1.1 kilo ohms, two significant figures, and measure the voltage and find it to be 4.7 volts, two significant figures again. In this case, what should be the reported current? The reported current should also have two significant figures, and the reported current should be 4.3 milliamperes, not 4.2727 or 4.273 milliamperes. It should be 4.3 milliamperes because we are dealing with two significant figures in our calculations and in our design. If a problem specifies that the measured voltage is 5.0, it is assumed that it is known to only two significant figures. It doesn't mean that it is exactly 5.00000. No, this means that it is known to only known to only two significant figures. It can be 5.04 volts, but it is reported as 5.0. So we are only sure about the two significant figures. We are not sure about the digits coming after our significant digits, and that's why they are not significant, because we don't know them exactly. We don't know their exact value. So I wanted to have this little bit discussion on what is significance, and also it is the other way around. Now sometimes you use lower number of significant digits in your calculations than actually required. That is also incorrect. For example, let's take this example that if your resistor is reported to be 1100 ohms or 1.1 kilo ohms, and your voltage is reported to be 4.7 volts, you calculate the current, so you have to report the current in two significant digits. If you write your answer as 4 milliamperes, that is wrong, because you are using only one significant digit. Why are you rounding off this significant digit? You never have to round off a significant digit. You have to use exactly the number of significant digits that are present in the values that are used for your calculation. You don't have to use more significant digits, and you never ever have to use even lesser number of significant digits that are available. Students have made this mistake in their quizzes, that we were dealing in three significant digits and they wrote their answer in one significant digit, so two of your significant digits were lost, and that is a loss of information, because we were sure about those two digits that were not included in your answer. Removing a significant digit from your answer makes your answer incorrect and unreliable. So it is correct both ways, that you shouldn't use either more or less number of significant digits than you can, and that number is the minimum number of significant figures that are used in your calculations. I hope this will help you in your future design problems. Now coming to noise and interference. We have talked about noise a lot in this course, that a noise was coming, so a common mode signal was coming at the inputs of the amplifier, and there is a common mode rejection ratio, and the common mode gain of an amplifier should be zero, of a differential amplifier should be ideally zero, and the noise can come in the two branches of a bridge circuit, and if they are equal in both the branches, then we can use the opposing branch to cancel out the noise, and so on. So from where that noise actually is coming from, that is the question. There are multiple sources of interference or noise, and they may be divided into four major types: electrically coupled noise, magnetically coupled noise, electromagnetic noise, and common mode noise. So electrically coupled interference or capacitive or high impedance interference is the situation where the signal of a nearby conductor is capacitively coupled to a nearby wire or cable, as shown in this figure. So here, this is your actual signal cable on which you are working right now, signal B. And there was another signal wire A that was passing nearby your signal B, your wire of interest. So between them, there is some medium. This medium can be air, this medium can be any solid or any other material. And both of these wires are conductor. So the material between these two wires, and as these two wires are carrying some electrical signal and they are conductors, so they will form a capacitor. a very low value capacitor, but still they will form a capacitor between them, and they will be capacitively coupled. Its impedance will be very high, but still they will be coupled capacitively together, and the signal from this wire will be transferred to the signal wire A, and the signal from wire A will be transferred to wire B, will be coupled to wire B, and this is called electrically coupled interference. The magnitude of that signal coupled from wire B to wire A is very small. That is why it is called interference or noise, but still it is sometimes significance if the value or the magnitude of the actual signal was also very low. That would be considered as a significant noise. And this signal wire A is usually your 120 VRMS or 240 VRMS power line, and that is a huge magnitude. So a significant amount of that signal, that power signal, is coupled to your other smaller circuits or high frequency circuits, and this is the equivalent circuit of that. So it looks like a high pass RC filter. So only AC noise is coupled, DC noise is not coupled electrically. And the magnitude of this coupled noise increases when the capacitance between the source and the pickup noise increases, or the frequency of the voltage source increases, or the level or magnitude of the voltage source increases, or the input impedance of the pickup circuit increases. This pickup circuit has an input impedance R. If this increases, or this increases, or its magnitude increases, or its frequency increases, in all these cases the magnitude of noise or interference coupled to your circuit will increase. So if any of these four increase, the coupled noise to our actual circuit will increase. So there is a clear message here. To reduce the coupled noise, we have to reduce these fours. But to minimize the noise, it is usually impossible to reduce the source magnitude and source frequency, because that source is some other source. That interference is coming from some other source. So we cannot mess with that other source. We cannot mess with the magnitude of that source, and we cannot change the frequency of that source. So it all comes down to these two things, number 1 and number 4. We can reduce the capacitance between the source and the pickup circuit to reduce the noise, or we can reduce the input impedance of the pickup circuit to reduce the noise. Now, how to reduce the capacitance between these two? Shield it. Use some material between these two so that the capacitance decreases. Increase the distance, because C is equal to A epsilon over D. So if you increase the distance, then the capacitance will automatically decrease, and that will result in lower coupling, capacitive coupling. Or you can twist the wires like this, and that will reduce the capacitance. So there are many ways to reduce this capacitance. To reduce the input impedance of your pickup circuit or your actual circuit in which your noise is being induced because of some other source, we will have some disadvantage. Just think about that. What would be that disadvantage? What should be the ideal input impedance of any circuit? We discussed that. The ideal output impedance is what? Either it is 0 or infinity, and the ideal input impedance is either 0 or infinity. So if we reduce the input impedance of our circuit, it may result in loading issues, because the ideal input impedance of our systems are usually infinity, to avoid making it as a load on our previous cascaded stage. And that's why we want to keep our input impedance as high as possible. So there is a trade-off. And usually this means that the capacitive shielding is the most appropriate method to reduce this capacitive coupling, because we should not reduce our input impedance of our design circuit Otherwise, there can be design issues with that circuit itself. Now, moving on to the next type of noise or interference, that is magnetically coupled interference. And when a current flows in a conductor, a magnetic field surrounds that conductor. And if a time varying current flows in a conductor, then the magnetic field that results will also change. So magnetically coupled or inductive low impedance interference arises from such magnetic fields created from current carrying conductors as described above. Normal sources of these noise are from power transformers, the power cord wires, and large ground loop circuits, or your inductive loads like heavy machinery, motors, etc. The coupling between the source of interference and any pickup circuit is inversely proportional to both the frequency and the distance. For frequencies below 1 MHz and the distance is less than 2 feet, the coupling impedance can be in the order of a few ohms, and that is really low value. And that means an excellently coupled interference. So the possible solutions for reducing the inductive interference include the use of low current and high impedance levels, larger spacing, short current carrying conductors, and eliminating low frequency response. However, many of the possible remedies for inductive interference actually increase the level of capacitive interference. That is an issue. So both types of interference may be reduced by increasing the distance between the noise source and the pickup point as well as proper shielding. So increasing the distance and shielding your circuit are the only two solutions that are applicable to both capacitive and inductive coupling to eliminate these noise. Otherwise, if you try to reduce the capacitive coupling, you are increasing the inductive coupling and vice versa. Magnetically coupled interference is more difficult to shield against, however. For power cord wires, twisting the wire pair minimizes the magnetic field surrounding the wires by reducing the area between the conductors, which reduces the induced current. So again, this approach of twisting the wires will shield against the magnetically coupled interference. The third one is electromagnetic interference, EMI. That is the most common form of noise that is present, that is surrounding us. Capacitively coupled interference produces an electric field. Magnetically coupled interference creates a magnetic field. In the region near the electric charge or current carrying conductor, or the field variation will be synchronized with the variation in charge or current. And when this is the case, the field is referred to as near field or induction field. At points farther away, the effect of near field is small and the electromagnetic field propagation predominates in what is termed as far field or plane wave propagation. You will study about these in your EMT course and then your wave propagation course. So I'm not going into the mathematics or details of that. So electromagnetic fields are created by a high frequency energy associated with radio waves or RF, radio frequency radiation. Besides the obvious situation of a radio station transmitter, RF signals are also produced by electric motors and generators, microwave ovens, remote control, garage door openers, radar detectors, and oscillator circuits in our televisions, radios, LCDs, and so on. Even the oscillator of your microprocessor in your CPU, in your computer. So there is an RF radio frequency radiation surrounding us, our mobile signals, our Wi-Fi signals, everything. And as its name suggests, the electromagnetic field simultaneously contains both electric field component and a magnetic field component. And since one thing to note here is that since EMI is caused by high frequency RF sources, many types of circuits are subjective to both capacitive and inductive interference. However, if either the magnetic or electric field component is effectively reduced, either one of them, then the electromagnetic field overall is reduced. That is the advantage. So generally a metal wire mesh is used as a shielding material like this, a metal wire mesh. And again, that is done using shielding your sensitive circuits. And if you have happened to open your cell phones, your mobile phones, you will see that there are certain components of your mobile phone that have a silver metallic casing or an enclosure like this. So these circles are the holes and this is a metallic case. So this is effectively shielding your sensitive components of the circuit from that EMI, electromagnetic interference. Then we have ground loops. Ground loops can be created by a potential difference between two or more points of a ground plane to which the external grounds are connected. That can be due to the inductive coupling of different points of ground with different sources of noise, capacitive coupling, and common mode noise. So this is a ground loop. There is a ground wire. It is connected to the ground plane or the earth at one point and at the second point also, but these 2 points were not at the same potential. So one was at higher potential, one was at lower potential, and there will exist a potential difference between these 2 points, and the current will start flowing through this plane and this wire, and it will form a ground loop. And then we have common mode noise that can be explained through this diagram. So if your signal source is connected to ground at one location and your amplifier is connected to ground at another location, and these two locations are not at the same potential, there exists a potential difference. So your effective input voltage of that amplifier would be the sum of your signal source voltage plus that difference, this VCM, the common mode input, that is the difference between the potentials of these two different locations of ground. The reduction or elimination of ground loops and common mode interference in equipment powered by power lines is achieved in one of the two ways: single point grounding and use of differential amplifiers. And we know both of these. So just connect all your circuit inside a circuit. So your grounds, this point is should be ground, this should be ground, this should be ground, this should be ground. Connect them all together and then connect them to ground at just one point. Don't ground this separately, don't ground this separately. Connect them all together and ground at a single point. And the second one is use of differential amplifier that automatically rejects the common mode signal. For a differential amplifier of this figure, R1 is 1 kilo ohm, R2 is 100 kilo ohm. If both inputs are tied together and the input common mode signal of 2 VRMS produced an output of differential amplifier of 0.08 volts, determine the common mode rejection of the operational amplifier. Okay, so R1 is 1 kilo ohm, R2 is 100 kilo ohms. This is 1, this is 100. So we can see from here that the gain is 100, the actual gain. This is the actual gain. And he's saying that the common mode signal of 2VRMS, this is the common mode signal, and it is 2V, and it produces a differential amplifier output of 0.08. So ACM will be equal to 0.08 over 2, and a diff is equal to 100. So this implies that CMRR is a diff over ACM, a diff over ACM, and that is equal to 2500. So it has a fairly good common mode rejection ratio. Now finally we have ground faults. What are ground faults? What is a ground? What is an earth? A ground fault refers to the return of a current to ground by any path other than the neutral wire. Here we have a power transmission line that is connected to our load. So we have a hot wire, that is a live wire. Then we have a neutral wire, and then we have a ground wire. So what happens is the current enters the circuit from the hot wire, flows through your load, leaves the circuit through your neutral wire, and then at the grid station it goes to the ground. So this is the normal case. When the fault occurs, when the ground fault occurs, the return path here you can see that it is disconnected. So the current will enter from the hot wire, it will go through the load, and it will not have any path to return through the neutral wire. Your instrument did not was not providing the return path through the neutral wire to the current, but rather the current was going to ground using some other path than the neutral wire. So what is this second path? Let's first see that. The current always follows the shortest path and the path with least resistance. So if this wire was connected like in this case, the current will follow the shortest path, that was the wire, the path of least resistance, and that wire was directly connected through the neutral line and it was being grounded. But what if some error, some fault occurred and this neutral line was disconnected? Now the current has nowhere to go. So your load will remain open and it will not operate. But a charge will accumulate at the body of your load. But your load will not be powered up. You will turn on the switch. It will be connected to the hotline or the live wire. But the current is not having any return path. Let's assume that this is also not present right now. So your load will remain open. But the issue will occur when a person will come and it will touch the load. So as soon as the person touches the load, now the current has been provided an alternate path to the ground, because this person is standing on the ground and his feet are grounded. So the current will try to complete its loop and it will enter the body of the person and it will go to the ground, resulting in current flow across the body of this user, and this user is going to get an electric shock. That is dangerous. All the current will pass through this user if there is a ground fault, if the current has no return path through the neutral line. So what do we do to protect against these kinds of hazardous situations? We connect this line, we earth our loads, and we connect our loads to the ground using a wire, and we connect this earth terminal to the body of that load. So this is the body of that load and its body is now connected to earth. So this will be connected to earth. The earth will not be connected in this circuit path. So what will happen now is, if there is a ground fault and there is no return path for the current through the neutral line, your current will enter, it will go to the load, it will not have any path to flow further. So your body will be charged and that charge will be grounded through the least resistance path available to it, and that is your earth wire that is connected to the body of that terminal. So even now if this user is going to touch this metallic body of this load, he will not get an electric shock because the current is going to follow the least resistance path, and the least resistance is not provided by your body. Your body has a huge resistance, it will be provided by this earth wire. So that is one thing that has to be kept in mind while using high power devices and working with the main lines. The second thing is that, okay, we protected our user from the harmful effects of getting an electric shock by touching the body if there is a ground fault. But that ground fault needs to be detected at earliest because it can damage your load also if the earth current is flowing, because it is inducing some common mode signal or common mode noise inside that load. So that fault needs to be detected and your load has to be completely disconnected from your line. So how to detect that ground fault and how to automatically disconnect your circuit from your AC power line? So this is a simple circuit that is used to perform this tripping operation. You have a hot wire and it is wound across a bead, a ferrite bead, toroid, and it goes to your AC load. This is your load. And then if everything is fine, these switches are closed, the current will return from another coil to the neutral and everything seems perfectly fine. A magnetic field is produced by this coil. A magnetic flux is produced by this coil. They are magnetically coupled, electromagnetically coupled, and their fields will be equal because the current entering a circuit is equal to the current leaving the circuit. So both of these currents are same, the fields will be same, and they will cancel each other out. So nothing will travel and nothing will be coupled to this third coil. But if there is a ground fault, let's say your load and your neutral wire were disconnected, so there will be no return current, no path for the current to return. And in this case, if your load was connected to the ground either using an earth wire or through a user, as soon as the user touches this, the load will be grounded and some current will flow through this path or through this path to the ground. But no current will return from the neutral line because now the current is not following this path through the neutral line. So there will be zero current here and there will be some current X passing through your live wire. So the flux produced by this coil, this live wire, will not be cancelled by this neutral wire now, and it will be coupled to this relay. And this relay will operate. It is normally in closed situation, but as soon as a signal is given, electromagnetic signal is given to its input, it will turn the circuit open. So it is also a detection circuit and a protection circuit. How? What if your load also had a fault and you did not connect the earth to the body of that load, and there was also some short circuit inside the load that was connecting your live wire to your load's body, and then when the user is touching that circuit, it is directly connected to the live wire and the current will flow from here to here to here, and it will be just like putting your finger inside the socket, and you may get stuck to that if it is a fairly high voltage. But as soon as even a few milliamperes of current start passing through this and no current returns, this relay will make this switch to trip and the circuit will be opened and the user will get a small shock. But as soon as he gets a small shock, the circuit will be opened and the user will be released from that load. So that is also serving as a protection circuit and also a detection circuit. So if this is tripping, there must be some ground fault in your load that has to be detected. So that was it about the additional concepts related to instrumentation. So at this point, your course contents for this course are finished. So congratulations. And from the next lecture, inshallah, we are going to solve the design problems related to different signal conditioning circuit design. So till then, take good care of yourself, stay safe, see you in the next live session, inshallah. Allah Hafiz.